Picture something simple. An electron meets a photon. Light scatters. It sounds ordinary, predictable, almost boring. A photon comes in, the electron absorbs it, continues on its way, and then releases another photon. This is how light interacts with matter. It's taught in textbooks. It's measured in laboratories. It's one of the most basic processes in physics. But when physicists sit down to calculate this simple interaction, something strange appears. Something deeply unsettling, because the mathematics does not allow only one path. It allows all possible paths, and some of those paths make no sense at all. But what happened next changed everything. When we draw the diagrams that describe this interaction, we must include possibilities that defy common sense. For example, the electron might emit a photon before it absorbs one. Already strange. How can something emit energy it hasn't yet received? But the mathematics insists. And then there is something even more bizarre. A possibility so strange that for decades physicists struggled to accept it. In this scenario, the electron emits a photon, then travels backward in time, absorbs a photon in the past, and finally turns around and moves forward in time again, backward in time, not as a metaphor, not as a mathematical trick, but as something that produces measurable effects in real experiments. This backward-moving electron is not hidden or imaginary. Its path can be long enough to leave a detectable signature in laboratory measurements. It contributes to outcomes we can calculate, predict, and verify. This is not philosophy. This is physics. When we calculate scattering probabilities, we must include these backward-in-time paths, or the answers come out wrong. Think about that. Reality itself demands that we include particles moving backward through time. Now here is where it becomes even stranger. When you observe this backward-moving electron while your own time flows forward, it does not look exotic or ghostly. It looks almost exactly like a normal electron. Almost. There is one crucial difference. Instead of repelling other electrons, it is attracted to them. It behaves as if it carries a positive charge. In other words, when an electron moves backward in time, it appears to us as a particle with the same mass but opposite charge. This particle has a name, the positron. The positron is not just some theoretical invention. It is real. It can be detected. It leaves tracks in particle detectors. It bends in magnetic fields exactly as a positively charged particle should. And yet, according to the mathematics, it is nothing more than an electron moving backward through time. This idea sounds outrageous, but it works. Every calculation agrees with experiment to astonishing precision. Now, long before anyone ever spoke about particles moving backward in time, a physicist named Paul Dirac encountered something deeply troubling in his equations. When he combined quantum mechanics with special relativity, the math predicted negative energy states, solutions that seemed physically impossible. Instead of rejecting the equations, Dirac trusted them. He followed the mathematics wherever it led, and what it led to was a shocking prediction. For every electron, there must exist another particle with the same mass but opposite charge. At the time, no such particle was known. The prediction seemed absurd, yet Dirac insisted it must exist. In 1932, Carl Anderson discovered it in cosmic ray experiments. The positron was real. The mathematics had predicted reality before reality revealed itself. This discovery changed physics forever because it didn't stop with electrons. If electrons have antiparticles, then so must protons. So must neutrons. So must every particle in nature. Every particle has an amplitude, a possibility to move backward in time, and every backward moving particle appears to us as an antiparticle. Matter and antimatter are not separate creations. They are the same entities viewed from opposite directions in time. And here is the most important rule of all. When a particle and its antiparticle meet, they annihilate, not collide, not bounce. They annihilate. Their entire mass is converted into energy, pure energy. For an electron and a positron, this energy usually emerges as gamma-ray photons, the most energetic form of light. Nothing remains, no fragments, no debris, just radiation. This is Einstein's equation made real. E equals mc2. Mass is not destroyed, it is transformed. Now, people often misunderstand what anti really means. They think it simply means opposite charge, but charge is only one property among many. Antiparticles differ in a whole set of quantum properties, and the true defining feature is not charge, it is annihilation. Bring two electrons together and they remain two electrons. Bring an electron and a positron together and they disappear in a burst of energy. That difference matters, and it leads us into something far deeper. Because once we accept that antiparticles exist, a question becomes unavoidable. If particles and antiparticles are so perfectly matched, why does the universe contain almost entirely matter? Why didn't matter and antimatter annihilate completely at the beginning of time? To answer that, physicists were forced to confront another assumption they had taken for granted, that the universe treats left and right the same. And that assumption turned out to be wrong. But that is where the story truly begins. For a long time, physicists believed something very simple. The universe does not care about left or right. Flip a physical system in a mirror, and the laws of nature should behave exactly the same. A right-handed world and a left-handed world should be indistinguishable. It felt obvious. It felt inevitable. And for decades, no experiment suggested otherwise. But what happened next changed everything. In the mid-20th century, physicists were studying a subtle process known as beta decay. This is a type of radioactive decay governed by the weak nuclear force, one of the four fundamental forces of nature. Beta decay looks harmless enough. A neutron inside an atomic nucleus transforms into a proton, releasing an electron and an invisible particle called a neutrino. Nothing dramatic, nothing explosive. But hidden inside this quiet process was a shocking secret. To uncover it, scientists designed an ingenious experiment using cobalt-60, a radioactive isotope. The idea was simple but technically demanding. If left and right are truly equivalent, then electrons emitted during beta decay should fly out equally in all directions. No preference, no bias. To test this, researchers aligned the spins of cobalt nuclei using a strong magnetic field. Then they cooled the entire setup to nearly absolute zero, so the nuclei would stay aligned. This was not a thought experiment. This was real, painstaking laboratory work. When the experiment was run, physicists watched carefully to see where the electrons went, and they froze, because the electrons showed a preference. They favored one direction over the other. Left and right were not the same. The universe itself had chosen a handedness. This discovery was devastating. A cornerstone assumption of physics had collapsed. Parity, the symmetry between left and right, was violated by nature. The weak force did not respect mirror symmetry. This wasn't a small correction. It was a fundamental betrayal. For decades, physicists had assumed the universe was perfectly ambidextrous. Now it was clear the universe has a dominant hand, and that raised an immediate question. If left and right are not equivalent for matter, what about antimatter? At first, physicists hoped antimatter might restore the balance. Perhaps matter violated left-right symmetry, but antimatter violated it in the opposite way. If that were true, symmetry might still survive in a deeper form. To test this, scientists repeated beta decay experiments, but this time using positrons instead of electrons. And what they found was astonishing. The asymmetry flipped. Matter on the right behaved the same way as antimatter on the left. The symmetry wasn't gone. It was hidden. This led to the discovery of a deeper rule called CP symmetry. C stands for charge conjugation, swapping matter with antimatter. P stands for parity, swapping left with right. Individually, both symmetries are violated, but combined together, the universe obeys them. If you flip both matter into antimatter and left into right, the laws of physics remain unchanged. This realization was breathtaking. Nature had not abandoned symmetry. It had simply buried it deeper. The universe is not simple. It is subtle. And this subtlety has profound consequences. Because once physicists understood CP symmetry, they realized something unsettling. If matter and antimatter were created in perfectly equal amounts at the beginning of the universe, and if their behaviors were almost but not quite symmetrical, then even a tiny imbalance could decide the fate of everything. A slight preference, a tiny asymmetry. enough to leave behind a small excess of matter after all annihilations were complete, and that tiny excess would become stars, galaxies, planets, life, us. In other words, the reason anything exists at all may trace back to the weak force violating symmetry by the smallest possible amount. Existence itself may be the result of a cosmic imperfection. Now, here's where the story becomes strangely practical. Imagine trying to communicate with an intelligent civilization light years away. You exchange mathematics, you exchange physics. Eventually, you want to define something simple, right and left. But space has no up or down, no shared orientation. How do you define handedness using only physics? Before the discovery of parity violation, this was impossible, but now it can be done. You instruct the aliens to build a cobalt-60 experiment, align the nuclear spins, measure which direction the electrons prefer to go. That direction defines right, pure physics, no ambiguity. But here's the terrifying twist. If the aliens are made of antimatter, they will get the opposite answer. Their right will be our left. And that difference matters, because when matter and antimatter touch, they annihilate. A simple handshake would not be a greeting. It would be a catastrophe. All that mass would convert into energy in an instant. Gamma rays, particle showers, nothing left behind. This is not science fiction. It is a direct consequence of symmetry, antimatter, and the laws of physics. So before you ever shake hands with an alien, check the beta decay experiment. What seems like abstract theory suddenly becomes a matter of survival, and all of it flows from one astonishing fact. Particles do not just move forward through time. They are allowed to move backward, and when they do, they appear to us as antimatter. To understand why this idea works so perfectly, why it explains annihilation, creation, and the deepest symmetries of nature, we must return to the mathematics, to the paths particles are allowed to take, including the ones that double back through time itself. At first glance, the idea sounds impossible. Particles moving backward through time. It feels like science fiction, a trick, a metaphor. But in physics, ideas are not judged by how comfortable they feel. They are judged by whether the equations demand them. And in this case, the equations do. This story begins with a problem that haunted physicists in the late 1920s. Quantum mechanics was working beautifully, but it had a blind spot. When scientists tried to combine quantum theory with Einstein's special relativity, things started to break. Electrons refused to behave. Paul Dirac set out to fix this. He wanted an equation that described electrons correctly while respecting relativity. When he finally found it, the mathematics was elegant, powerful, and deeply unsettling. The equation predicted negative energy states, not small corrections, not rounding errors, entire states with energies lower than anything physicists had ever imagined. At first, this seemed absurd. If electrons could fall into these negative energy states, they should keep falling forever, releasing infinite energy. The universe would be catastrophically unstable. But Dirac didn't dismiss the equation. He trusted it. Instead, he asked a different question. What if these negative energy states are already filled? He imagined a vast sea of electrons occupying all negative energy levels. Ordinary electrons couldn't fall into them because of the Pauli exclusion principle. This idea was strange, but it worked. And then came the boldest step of all. If one of those negative energy electrons were knocked out of the sea, it would leave behind a hole. And that hole would behave like a particle. Same mass as an electron. Opposite charge. Dirac had predicted antimatter. Not by speculation, not by philosophy, but by following the mathematics wherever it led. A few years later, Carl Anderson observed exactly such a particle in cosmic ray experiments. The positron was real. Reality had obeyed the equation. But Dirac's interpretation wasn't the final word. Richard Feynman, always uncomfortable with unnecessary machinery, looked at the same mathematics and saw something simpler. Those negative energy solutions, they could be reinterpreted. Instead of particles with negative energy moving forward in time, they could be particles with positive energy moving backward in time. Same equations, same predictions, cleaner picture. In this view, antimatter isn't exotic. It's ordinary matter, seen in reverse time. When an electron appears to annihilate with a positron, what's really happening is a single electron reversing direction in time. What looks like creation and destruction is actually one continuous world line, a path that bends backward then forward again. And here's the key point. This isn't philosophical wordplay. Every calculation in quantum electrodynamics relies on this interpretation. Every Feynman diagram includes paths where particles move backward in time. Physicists don't avoid these paths. They must include them. When they do, the predictions match experiments to astonishing precision. 1 part in a trillion. No other theory in science comes close. Nature is not politely ignoring backward time paths. It is using them all the time. When photons collide and create an electron-positron pair, that's a backward time segment appearing in our forward time view. When particles annihilate, that's the same segment turning around again. From our perspective, particles appear and disappear. But from the deeper mathematical perspective, nothing is ever created or destroyed. There is only motion, forward, backward, and curved through time. This explains something that once seemed mysterious. Why must every particle have an antiparticle? Because the equations allow motion both ways in time. Once you allow that, antiparticles are unavoidable. Photons, interestingly, are the exception. A photon moving backward in time looks exactly like a photon moving forward. No charge, no distinction. That's why the photon is its own antiparticle. The rule is universal. The exception proves it. Now think about what this means. The universe is not built from particles popping in and out of existence. It is built from continuous paths, world lines weaving forward and backward through time. Annihilation is not destruction. Creation is not birth. They are illusions produced by our one-way experience of time. We are stuck moving forward. So when we see something moving backward, we give it a new name, antimatter. This picture feels radical, but it works. It explains symmetry. It explains annihilation. It explains why the equations demand antiparticles. And it sets the stage for something even deeper. Because once you accept backward time paths, you are forced to confront a disturbing question. If the laws of physics allow time to run both ways, why does our experience not? Why do we remember the past but not the future? Why does the universe have an arrow of time at all? And more importantly, could this asymmetry be connected to why matter dominates over antimatter? To answer that, we must look beyond particles, beyond equations, and into the earliest moments of the universe itself. Up to this point, the universe seemed fair. For every particle, an antiparticle. For every process, a mirror process. Forward and backward in time, woven into the same mathematics. Balance, symmetry, and for a long time, physicists believed this balance was perfect. Left and right should be equivalent. Matter and antimatter should behave the same. The universe, they assumed, had no preference. But then came an experiment that shattered that belief. In the 1950s, physicists were studying a particular kind of radioactive decay known as beta decay. Certain nuclei, like cobalt-60, decay by emitting electrons. According to everything physicists believed at the time, those electrons should be emitted equally in all directions. Left or right should not matter. But when scientists actually performed the experiment, something shocking happened. The electrons preferred a direction. They favored one side. Left and right were not the same. The universe had chosen. This discovery stunned the physics community. For decades, parity and the idea that mirror images behave identically had been considered sacred. No one seriously questioned it, and yet nature did. The weak nuclear force responsible for beta decay violated left-right symmetry. The universe distinguished between clockwise and counterclockwise, between left and right hands. This wasn't a small correction. It was a fundamental crack in our understanding of reality. But the shock didn't end there. If left and right are different for matter, what about antimatter? Physicists assumed that antimatter should behave like a mirror version of matter. If matter violates parity, antimatter should violate it too, but in the same way. That assumption turned out to be wrong. When experiments were performed using positrons instead of electrons, something remarkable emerged. Matter on the right behaved the same as antimatter on the left. The symmetry hadn't vanished. It had been hiding. You couldn't restore symmetry by flipping space alone. You couldn't restore it by switching matter to antimatter alone, but if you did both at once, flipped left to right and matter to antimatter, the universe became symmetric again. This combined symmetry is called CP symmetry, charge conjugation plus parity. A deeper rule, a more subtle balance. The universe does not respect left and right individually. It does not respect matter and antimatter individually. But together, it almost does. And that word, almost, is where things get dangerous. Because CP symmetry is not perfect. In rare processes involving certain particles, even this combined symmetry is violated, just slightly. But that slight violation may be the reason you exist. According to everything we know, the Big Bang should have produced matter and antimatter in equal amounts. If that had happened, they would have annihilated each other completely. The universe would be filled with light and nothing else. No stars, no planets, no life. Yet here we are, which means something tipped the balance. Something favored matter over antimatter by a tiny amount, about 1 extra particle per billion. That tiny excess survived annihilation, and everything we see today is built from it. Galaxies, atoms, your body, all trace back to that asymmetry. CP violation is one of the leading explanations, a small imperfection in the laws of physics amplified by cosmic time. This connects antimatter, time, and existence itself. The arrow of time, the dominance of matter, the reason the universe didn't erase itself. They may all be linked. And this brings us to a surprising, almost humorous consequence of these deep ideas: communication with alien civilizations. Imagine humanity makes contact with an intelligent species across the galaxy. We exchange messages, learn each other's languages, share physics. Eventually, we decide to meet. But there's a problem. How do you define left and right across empty space? There's no universal up or down, no shared reference frame. Before parity violation was discovered, it would have been impossible. But now we know a way. We can describe a beta decay experiment, align the nuclear spins, cool the system, observe which direction electrons prefer to emerge. That direction, that's what we call right. Pure physics, no conventions. Now imagine the aliens perform the same experiment. If they get the same result, they're made of matter like us. If they get the opposite result, they're made of antimatter. And suddenly, a simple greeting becomes dangerous. A handshake could be catastrophic. Matter and antimatter touching would annihilate in a flash of gamma rays. A cosmic misunderstanding. Physics quite literally deciding survival. This may sound like science fiction, but it follows directly from real, tested laws of nature. Antimatter is not fantasy. Backward time paths are not metaphors. They are woven into the equations that govern reality, and they lead us toward an even deeper realization. Particles are not the fundamental story. Time itself may not be what we think it is. And to understand that, we must return to annihilation, to creation, and to the strange way the universe turns mass into pure energy. At the deepest level, the universe does something extraordinary. It allows matter to disappear completely. When a particle meets its antiparticle, there is no debris left behind. No fragments, no ash, no remnants, just energy, pure, radiant energy, racing away at the speed of light. This is annihilation. An electron meets a positron, and both vanish, replaced by gamma rays. Their entire mass converts directly into energy, exactly as Einstein's equation predicts. Nothing is lost, nothing is gained, only transformed. This is not destruction, it is bookkeeping, nature balancing its accounts. And what's remarkable is that the process works perfectly in reverse. If you concentrate enough energy into a small enough region of space, that energy can turn back into matter. A photon can split into an electron and a positron. Creation and annihilation are not opposites. They are the same event seen from different directions in time. This happens constantly in particle accelerators, in cosmic ray collisions, near neutron stars and black holes, even high above your head as cosmic radiation strikes Earth's atmosphere, briefly creating particle-antiparticle pairs before they vanish again. The universe is doing this dance all the time, mass to energy, energy to mass, forward and backward through time. And here's the profound realization. From the deepest mathematical perspective, particles do not pop in and out of existence. There is continuity. A single electron's world line can loop backward through time, then forward again. What we call a positron is simply that electron seen moving the wrong way in time relative to us. Creation is a U-turn. Annihilation is the same U-turn seen from the opposite side. Nothing mystical, nothing supernatural, just geometry in space-time. This picture explains why quantum electrodynamics works so astonishingly well. Every Feynman diagram sums over all possible paths. Straight ones, curved ones, even those that run backward in time. When we include them all, the theory predicts reality with almost unimaginable accuracy. 1 part in a trillion. Nature agrees. Again and again. Now consider what this means philosophically. We experience time as one way, past behind us, future ahead. Memory flows in only one direction. Cause precedes effect. But the laws of physics do not care. They allow time symmetry almost everywhere. The arrow of time does not come from the equations of particles. It comes from something else, from entropy, from the universe's initial conditions, from the fact that the early universe was in a remarkably low entropy state. Time flows forward for us not because the laws demand it, but because the universe began that way. At the microscopic level, the universe is almost indifferent to time's direction. Particles don't know which way time flows. They obey the equations, and the equations allow both. This reframes one of the oldest questions in physics. Why does the universe exist at all? Why didn't matter and antimatter simply annihilate completely in the first moments after the Big Bang? Why is there something instead of nothing? The answer may lie in tiny asymmetries, small violations, imperfections in symmetry so subtle they took decades to discover. CP violation, a slight preference for matter, just enough to tip the balance, just enough to leave behind 1 extra particle per billion. That tiny excess became galaxies, stars, planets, life, you. The universe as we know it is the fossil record of a broken symmetry, and antimatter is the shadow that symmetry left behind. This is why antimatter is so rare today. Not because it's forbidden, but because it lost by the smallest margin imaginable in the earliest moments of cosmic history. Yet its imprint remains everywhere, in equations, in experiments, in the very structure of reality, and perhaps most importantly, in what it teaches us. Antimatter shows us that reality is not made of solid objects. It is made of processes, paths, relationships, motion through space-time. Particles are not things, they are events. And time itself is not the rigid backdrop we once imagined. It bends, it loops, it allows matter to retrace its steps. The universe is far stranger and far more elegant than common sense would suggest. When we look closely enough, we find that what appears as creation and destruction is really continuity. What appears as difference is symmetry in disguise. And what appears as chaos is mathematical necessity. Sometimes the universe whispers its secrets. Sometimes it shouts. Antimatter does neither. It simply exists, quietly obeying equations that allow matter to move forward, backward, and sideways through time. And by understanding that, we glimpse something profound. Reality is not built the way we intuitively think. It is built the way mathematics demands. And that is what makes physics beautiful.